It's cruise control, except the motorway is covered in boulders and sand traps.
You're listening to The Cosmic Cast.
Hello everyone, and welcome back to another episode of The Cosmic Cast, brought to you by the Earth and Solar System Group at the University of Manchester. You're here with me, Ricky. We're here with John, Bernard Fisher, Marissa Lowe.
Hello.
Elliot Carter.
Hello.
And we've got a great guest for you all today. We've got Dr. Elliot Sefton-Nash.
Hello.
And this is actually your second time we've had you on. We saw you in person the first time, and was it 2 years ago now, or is it only just over a year
ago? Just over a year ago
now.
Yeah.
I don't even remember.
Most people try to force it out of their mind.
That's true.
It's often common to forget.
Yeah.
These days, time is much more abstract than usual.
Well, yes, indeed. So I take it you're in lockdown as well.
Yep, very much. It's been kind of a blessing, kind of a burden. It's one of those like, oh, this could be a mini sabbatical, but then it turns out to really not be that, because there's all kinds of excuses to actually be more productive than if you are on site.
So just so the listeners know, you work at STEC, which is the European Space Agency's department in the Netherlands. And your position currently there is?
Well, my job title is a planetary scientist. The role is a project scientist. So you're basically the interface between the projects that build and operate the spacecraft and the science community who get the benefits from it. So it's kind of like a meta science, diplomat science type role, but you find yourself in the middle of a lot of situations pushing in all directions.
And have you been having to do a lot of management at home at the moment then with people?
Yeah, well, it's also quite a tricky interface in many directions, because you're not necessarily managing people directly, but you kind of have influence in some ways. So you have to try and figure out how to convince people or show them some evidence that what they're suggesting is a good idea or a bad idea, and but yeah, I mean, my day is at least 50% meetings, so I am no stranger to Zoom.
How are you finding that? Because we find even at our department, I have very few Zoom meetings, I imagine, compared to you, very, very few, and I find them exhausting.
They are,
So.
Yeah, they can be. I think you can get WebEx or Zoom fatigue. Just the process, it really ruins wearing headphones for me. When I want to listen to music, I'm like, oh, this means work. Yeah, and it's difficult as well because you don't necessarily have the face-to-face interaction. You can't just stand by the water cooler, have a coffee, and have a casual chat. There's no bar afterwards. There are other kinds of tragedies associated. But these are obviously, very minor problems compared to the global pandemic that is making its way through the world. So I think you guys as well, consider ourselves quite lucky that we can do at least some work at home, even if your labs aren't fully operating.
Yeah, definitely a good time to catch up on papers. So are things starting to reopen again now?
Yeah, and I think a lot of big departments, big agencies are trying to be much more careful than the average. They're kind of waiting to see what happens with the various governments, particularly ones who operate in multiple countries. They don't want to take an approach that's any more risky than any one of their member countries. So ESA is no exception there. We've got this target of having, I think, 50% of people back by the end of September or something. But even then, the necessity of that really depends on what your job is. I am not an essential person to be on site, so I expect I'll be at home much longer than September.
Presumably it's all the sort of mission control people and a lot of the engineers and all the lab-based people then that'll be primarily
it's mostly people doing stuff in labs or doing testing. I think actually some of the operations and some of the mission control stuff you can actually do offline. I mean, if you can send commands to a spacecraft that's millions of kilometers away, then why can't you? Why can't you just be 10 kilometers away from your office and still do the same thing? So,
quite a thing to do in your pajamas, isn't it?
Yeah.
So how have different projects been affected by lockdown then?
Yeah. What? So you mean missions?
Yeah, the ones that you've been working on.
Yeah, I think.
I guess for context, we should say, I guess you're working mostly on a lot of Martian missions, aren't we?
Yeah, I'm kind of a mixture, although I'm transitioning to mostly do Mars stuff. So as of Wednesday this week, actually, I'm no longer the primary project scientist for Prospect, which is NASA's payload for looking at lunar volatiles at the poles of the moon, and it's scheduled to fly on the Russian Luna 27 lander. And there are also now some discussions about, how could Prospect potentially interface with the NASA commercial efforts to go back to the moon and send people eventually. So, so somebody's taking on Prospect, and I'm working mostly on ExoMars now. But I also support MMX, the JAXA mission, to go and look at the Martian moons. So yeah, right now I'm really focused on trying to get ready for ExoMars rover operations, which may seem like a long time in the future, but there's a lot to do.
Yeah, it's had a bit of a strange timeline, hasn't it? I've seen a lot of excitement on and off of launch dates coming up and then being pushed back.
Yeah, the perpetually forward-moving launch date is just the scourge of the space industry, and it's extremely difficult. Whenever you launch, there are always going to be things that you never had time to do. It's like writing a paper. It could always be better, however long you spend on it. So it's one of those things where you have to really try and keep check of the things that are critical to whether the mission is going to actually work or not. So yeah, I mean, as you know, the most recent delay was from 2020 to 22. And, that came after a long set of investigations that were incredibly carefully considered. A long time before anybody was talking in the public sphere about the potential shift to 22. There were already very detailed reviews underway to try and figure out if all the different parts of all the different systems could really be, counted on in terms of their development and testing. So there were many factors contributing to it. And then in the end, COVID-19 came along, and that was just the icing on the cake that really kind of, if it wasn't already heading towards the edge, it definitely pushed it over the edge. So, but 22 actually makes it a lot more tenable from a science planning perspective as well. Certainly I'm grateful for the time.
This might be a really simplistic question, but how do you know when it's ready?
Yeah, sure.
I've had that problem. You mentioned papers, and that's hard to know. How do you know with a rover?
You stick a skewer in it, and if it comes out, you're ready.
Yeah, you don't have a rover meat thermometer, you mean? Everybody had those. You basically have to set boundaries that are meaningful. When you design a test, and this is something that the industrial partners do day to day. They design a test. Okay, how do you record the outcome of the test? What does that outcome mean? What's the confidence with which you believe that outcome? And so all that has to be really characterized in detail and documented. And then when the tests are done and the results come back, you can say, okay, this is an acceptable risk. Because in the end, it's all about what risk you're willing to take. How much money are you willing to put on the line to when you launch this spacecraft, if it costs €1 billion, for example.
Yeah.
So what do you think you'll be doing with this 2 years then, now that we've got another 2 years before it's actually going to launch?
Yeah. Well, I think you know some of it, Ricky.
Don't give away the movie magic, Elliot.
Well, so there's a lot to do in terms of the science planning side of things. One of the big efforts that I'm trying to work on is developing testable hypotheses that we can then use to plan operations. So we know where we're going. It's Oxia Planum, a very flat but very interesting place on Mars. And we need to understand what features, what rocks, what mineralogy is there in terms of what that means for the mission's science objectives. So the rover mission has science objectives about astrobiology and about characterizing the subsurface. But the primary objective is looking for signs of past or present life. And so whatever measurements we do have to be in aid of that objective. So how do we know if we're following the right direction? Well, we have to, first thing we should do is figure out what rocks are there. So we need to make a geologic map. Once we have the map, then we have to figure out what other hypotheses about Oxyoplanum that would tell us something about whether or not there's past or present life. So which rocks should we sample? Once we know which rocks we should sample, then we can figure out, okay, if we land here, what's the probability that we'll get to sample this rock, in the first 10 sols of operations or something. We basically then have to do this whole process of weighing up all the possible traverses based on all the possible very precise landing positions, and come up with a plan so that when we come to land, we'll be able to say, okay, we're here now. So we know that if we go in this direction first, that gives us the highest probability of making some interesting discovery in the shortest time, with the shortest power, with the least amount of data, stuff like that.
I guess
So,
is there a bit of tug of war between the different instruments and on all the different PIs on different instruments in terms of who gets the amount of time? And I'm sure like some people would want more time, some people would want less time, and must be a bit of must be quite difficult to try and distribute an analysis time evenly across all instruments.
yeah. Well, that's kind of part of the role, I think. I think it's probably a fair statement that principle that whenever resources are scarce, everybody wants a piece. And rover time in terms of power or number of measurements you can take is definitely no exception. So I think one of the ways, at least the project scientists, Jorge Bargo and I are thinking about managing this is this is one mission with one set of science objectives, and it has one science team. It's not about your instrument or the other person's instrument. It's about how do we answer this question most efficiently. So it really is making everybody a team player. And one of the mechanisms that we can demonstrate that that's important is by having this map and this set of objectives that are traceable, because then we can say, okay, well, it's clear that if we go there first and measure this rock with that instrument, we've got the best chance, so we should do that. Yep. And everybody in this room was part of the process, so we all had a hand in it.
So what are the main instruments that are going to be landing there then? Would you mind talking us through the main experiments that are going to be done?
Sure, yeah. Well, the rover is not on its own. It gets delivered to Mars on the Russian surface platform, which is called Kazachok, which means little Cossack, I'm told. So the platform itself has, I think, 13 instruments, and actually I don't think I can name them all. But the rover has 9 instruments. So let's start from, I guess we'll start from the cameras. So the most visible thing that you would see when you see a news article about Mars is some pictures, and usually that's taken by some high resolution or panoramic camera. And the ExoMars rover, called Rosalind Franklin, has a PanCam, which has several different channels. It has a wide angle and a narrow angle part. And basically that will take the pictures that we will use for kind of navigating and also for science operations. There are also navigation cameras and location cameras with NavCam and LogCam, and there are pairs of those for doing the autonomous navigation the rover does. Those are not designed for science; they're more for the kind of operations side of things. So then there's an instrument called ISEM, which is an infrared spectrometer, which is co-pointing with the PanCam camera. So wherever you take a picture, you can also take an infrared spectra and look at the mineralogy of wherever you're pointing. So if we go down to the subsurface, so the rover has a drill, and the drill samples down to about 2 meters. And the idea with that is that the best chances of organic molecules being preserved are at depth, because they're not exposed to cosmic rays, they're not exposed to the very oxidizing surface chemistry and the daily thermal cycling and so on. So there's an infrared spectrometer in the head of the drill itself. So as you drill down, you can take infrared spectra of the borehole that you make.
Very cool. That's awesome.
Yeah, it's quite snazzy, yeah. And when you get the sample back, you can then take it into the inside of the rover. It's called the Analytical Laboratory Drawer, ALD. And that has three instruments. But before it gets there, it gets imaged by a very kind of like a geologist's hand lens. It's an instrument called CLUPI. It stands for Close-Up Imager. And then it goes inside the analytical lab drawer. It gets basically processed. There's a whole sample handling system. The sample gets crushed and then dosed into different ovens. Before it's dosed in the ovens, it gets imaged by an instrument called Micromega, which is an imaging spectrometer in infrared, and also a Raman spectrometer with RLS. Then there's also the option of it being analyzed by one of the kind of flagship instruments called MOMA, the Mars Organic Molecule Analyzer. And that's really where we learn about the composition that's relevant for past or present life. So it gives you all kind of molecular abundances, the chirality of the molecules, there's all kinds of fancy stuff. And two other instruments of interest are, there's a radar, subsurface radar, where we can basically try to get the structure of the subsurface as we rove along. And there's also a neutron spectrometer, which tells you something about the hydrogen content of the subsurface, which is obviously very closely linked to water. So I think I covered the 9. I'm not sure. I wasn't counting.
That sounds really cool. So I guess some of the American rovers have been operating for years now. Is there an anticipation that this might go on for maybe like 10 years or so as well, or is that funding dependent?
Yeah, it's always funding dependent. I think what you can say is that there's a nominal mission which has a very specific set of objectives.
Yeah.
And the rover has been designed around that. Mm-hmm. And so all of the operations sequences and all of the hardware components are designed at least to meet the nominal mission. But of course, they build in margins so that it should last much longer than that. Whether or not an extended mission is funded or not depends on the member states of ESA saying, yes, we want to keep funding the rover because it's doing amazing science, or maybe they have other priorities. So that has to come, and every mission goes through these cycles. And NASA missions have the same process. You have to write a proposal for a mission extension, and then it has to get evaluated, and then some high-level committee gives a thumbs up or not. But usually, if you've spent inordinate amounts of money sending a rover to Mars, you want to keep it running as long as possible. So I'm confident there'll be extended missions. Yeah,
that's really cool. Do you think you'll get to go to the launch? Is it presumably it's being launched in Kazakhstan?
Yeah, I'm actually not sure if I'll get to go to the launch site, because there's a few places you could be. Because the rover will be controlled from what's called the Rover Operations Control Center in Turin. But the spacecraft is, before that control center takes over, the spacecraft is controlled by ESOC, which is an ESA center in Darmstadt in Germany, where they fly all of these spacecraft. Some people will be at the launch site, but there will probably be events at all of those places. So I'm actually not sure which one I'll go to.
So,
I mean, it's a good situation to have too many parties,
right? So we've said you can already obviously plan out the map, and you can plan out which outcrops you think would be ones of interest to actually drive to and take samples of. But in terms of once the rover's landed, how quickly or how long does it take for the next day to be planned of operations? Is it already pre-planned? Do we know where it's landed now? Or is it a day-by-day type of activity?
Yeah, it's a really good question. So the first thing that happens after we land is there's a period of time called post-landing to egress. And that's basically where everything gets checked out in a really specific sequence. The rover's still on the platform at the start, and it has to deploy all these things and make sure it has enough battery power to get off, and all kinds of things have to happen. So that takes about 10 Mars days. And then once we're off, there's a few other things that have to happen in terms of commissioning instruments and making sure everything works on its own. But the nominal operations is basically a process that revolves around the uplink and the downlink of data to and from the rover. So when we get data back from the rover, immediately everything sets into motion, and there's what's called a tactical shift. And the tactical shifts are, there's a primary one which happens straight away after the downlink. And that's when everybody is, in action, processing all the data, looking at all the new stuff that's come back, and basically identifying new targets, new things that we might want to send for the rover to do in the uplink, which comes, a few hours later. So then there's that first tactical shift, which basically gets to an endpoint, and there's lots of discussion. There's lots of, each instrument team will have their own priorities, and there has to be several meetings where we boil down what's called an activity plan. Then the activity plan has to be kind of validated and verified to make sure the rover can actually do what we want it to do in the next sol. And actually, we make 2 activity plans. So we always plan 2 sols ahead, just in case we miss some overpass or the rover has a problem. At least it's still got commands for something to do, not just twiddling its robot thumbs for a day. So then there's a second tactical shift where basically everything is just checked and checked and checked, and then it gets uplinked to the rover. But the timings of those are not consistent with Earth days. They revolve around when we get data back from Mars. So the complexity there is that we also have what's called a strategic cycle, which is much more kind of office hours, and that will happen every single day. There will be people from all the instrument teams and the kind of general rover science team will be either in person at the control center or connected remotely, and we'll just talk about, okay, well, this is what we learned from these data that just arrived in that last tactical shift, and here's what we should do for the next week. We keep track of the long-term science goals, long-term objectives, figure out what to publish, what to announce. There'll be discussions in that meeting like, oh, this is interesting. So do we think it's life or not? So that's where the real meat of the science happens.
That's really cool.
Go on, John.
No, I was just going to ask, how many sort of people are involved in this process? Are we talking of teams of like tens of people or hundreds of people?
Yeah, I think it might be close to 100. So certainly at the Rock, on the science side, there'll be at least 2 people, probably several more from each instrument team. Over time, it might be that there will be less participation in person. People can connect remotely because it's expensive to go live somewhere else, and people have families and all kinds of other real life complexities. So I think in person during the first few weeks there'll be a lot of people there, and the remote participation will just become more the norm, I think, as the mission goes on. But even then, I mean, if we think about all the surface platform instruments and the rover instruments, there's a big science community that will need to communicate on a daily basis. So probably 100 people. And that's just on the science side. On the engineering side, there's a whole, probably even larger team who are dealing with making sure the rover still functions.
Yeah, I think the image you normally get of what mission control must look like from like sci-fi movies is, a room full of screens and computers and people running around lots. But I suppose for really long-term missions, like a rover going around for months, if not years, I imagine you can't keep that level of intensity up. People in mission control, shouting at each other and stuff. It must be quite a different process with, as you say, people getting the data more remotely, or splitting off into smaller teams, rather than it being, an Apollo movie.
Yeah, and it's it's kind of a bit saddening to think that at some point it might get just routine. Like there's nothing routine about this. But imagine we get multiple mission extensions, and every single day there has to be a strategic meeting for the next 5 years. That's when you think about it. Okay, I'm going to do the same thing every day for 5 years to run a Mars rover. I mean, that's extremely cool, but that's a long time. So there'll be shifts, and people will take holiday, and we'll have different people running different roles and stuff like that. To try and change it up.
Yeah, I think something we should point out to the listeners is obviously this rover has landed. Well, when it lands on the surface, as someone who's operating it, you don't see what it sees, so you haven't got like a live stream view on a camera of what it's seeing. So how do you actually figure out where exactly it is, and how are you going to drive it to a location where you're going to sample something?
Yeah, well, that really lies in all the software tools. So there's a big set of software tools that exist, and they allow you to do all kinds of planning and assessment. But most importantly, I think from the science point of view, is putting everything in context visually.
Mhm.
So it has the ability to put all the images taken by all the different cameras, in one 3D environment that you can just kind of move around and navigate, see where things are. There's a full software version of the rover model, so you can see where all the wheels are. If a wheel is stuck on a rock, the rock will be there because the rover makes terrain models using its cameras everywhere it goes. So we have a complete 3D environment to explore, just like a computer game. There's also something in the rock, kind of like a Mars yard with a Mars terrain simulator, and that has the like a ground test version of the rover, and that lets us test out specific conditions that we might find the rover in, just to see what it does. If put a rock here or put a sand area here and drive over it, how does it perform? And this can help us with operations planning.
Is that yard in Aztec? Sorry.
That one is actually in Turin.
Okay.
Is there going to be any like AI capabilities in it to avoid certain features or anything like that?
Yeah, so it has autonomous navigation, which I suppose you can call AI. Yeah, it's basically quite a highly developed algorithm that lets you assess the environment, try and figure out the risks. And so, the idea is that we send waypoints to the rover. We send it destinations, and it tries to drive there. The light time between Earth and Mars, it's obviously not constant, but at maximum it's like half an hour. So it's kind of like, okay, it's not really something you can do real time. It makes a lot more sense, and you can cover a lot more ground if the rover has the ability to navigate itself.
Cruise control.
Kind of, yeah. It's cruise control, except the motorway is covered in boulders and sand.
So I guess we should also point out that's why a flat area like Oxyoplanum is a good place for it to land, really, because obviously even small boulders can put it off, but big craters would be a real issue for it if it's going to roll into one of those. So you want somewhere flat, essentially.
Yeah, flat is good. Gives you the best chances of getting everywhere. Yeah, it's also safest for landing.
I guess a lot of people might be aware quite how slowly these sort of things move, don't they? I suppose what sort of distance do you think you'll cover over a couple of year period?
In a couple of, I think in the nominal mission, it will be on the order of a few kilometers.
Right. Okay. Yeah.
And that's in the first. The first Earth year. Okay.
So I guess it's easy to picture these rovers sort of whizzing around, but really, I suppose they really are just at a crawling pace, aren't they?
Yeah, and that's mostly. I mean, it's not safer to go much faster, but it's also a power constraint because you need to use a lot of energy to go fast. You also waste a bit more. So you can watch videos of the rover testbed, roving around, trying to autonomously navigate itself. But you can see it's really just a crawling pace. It's a few centimeters per second. But if you're doing that for many, many hours a day, you can cover quite a lot of ground.
Yeah.
And are you at all fearful that the rover will become sentient and it'll actually start to control you?
It has worried me a little. Yeah. The most recent concern was when I discovered that it wasn't that we named it Rosalind Franklin. So the name was selected via a competition.
One thing I was wondering is how, what are the things it's specifically looking for as signs of life? Like, what would be the smoking gun that this mission would find?
Yeah, that's a good question. It's something that I'm not a super expert on, but I'm kind of aware of a few potential smoking guns. So I guess the first thing is that, so everybody knows there are lots of signs of organic molecules that just form naturally in the universe anyway. So that's kind of the first thing that suggests, so actually, okay, smoking guns may not be actually that smoking. Amino acids form in comets. So one of the things that the MOMENT instrument can do is look at chirality. And so that's basically the left-handed versus right-handedness of molecules. And it turns out that life prefers one distribution of chirality over the other. So if you see that offset, I don't think people are aware of any natural processes that are not associated with life that would produce that difference. So that, I think that's one, I mean, that's specifically why MOMA does that measurement.
Yeah, right.
And the other thing is carbon isotope ratios. I mean, that's, you know, that's, again, it's all about kind of the physics of it. Life is quite lazy and prefers the lighter isotopes because it's not as much energy to move them around. And so if you see a carbon 12-13 ratio that's consistent with terrestrial carbon isotope ratios, you know, all the carbon in our bodies has some bias because of that. That would be another smoking gun.
Right.
Those are the two that I'm most confident talking about.
So I guess it's a case then of there was life rather than this specific type of life. It's still very much a generalized picture, what we'll see.
But in terms of biosignatures, there's a huge body of evidence that we kind of have to take piece by piece to build up a score, kind of a biosignature score. There's been controversy in the past about whether some, you know, chemical or physical discoveries were caused by life or not. For example, in meteorites, you know, people thought, oh, these minerals must have formed from an organic process, but it turned out actually you can form these from just a regular physical process, no life involved. So I think that's, that's why we have to have these very detailed strategic meetings about, okay, is this really a good thing to say about these results? It's kind of on the border. So we have to be quantified and purposeful in interpreting all that. How do you know if a Martian fossil is a fossil or not?
Yeah.
For example.
What aspect or big science question from the mission would you say you're most excited about?
Yeah, honestly, despite my comparative lack of understanding of detailed biosignatures, probably discovery of life. I mean, that's quite that's quite an irrefutably large objective. The potential to be involved in a mission that really, you know, digs deep and figures out if Mars ever hosted life. I mean, I think for me the big meaning of that relates to the Drake equation, because it pins down the number of planets in any star system where life could form independently. And given that we know that there are billions of planets in our galaxy alone, I think that will have the biggest impact.
Yeah.
So obviously you've been at home for a while now, and I hope for your sake that's allowed you to have more time to actually get involved in some of your research patterns. So is there anything you're researching at the moment that you find particularly interesting?
Yeah, there are a few things which I still don't have any time for, but remain interesting. So I think probably the one that's that's closest to being semi-finished is the best way to describe it. So in Mars's history, there were many large impacts, and some of them probably formed a debris disk afterwards, so a kind of transient disk of rubble that was orbiting. And it was probably orbiting Mars's equator, because dynamically that's where orbits tend to be stable over the long term. So also on Mars, there are some craters which have kind of an elliptical shape. And generally it's thought that those form from impacts at very low angles. So they come in quite shallow, and then they kind of they scoop up this very long crater compared to the normal round ones that we see on most planets. And that distribution of craters is formed by stuff that came in potentially just randomly, or it could have come from something that allowed them to have a shallow angle. And this could be a debris disk that was transient. So the idea then is to figure out how many of those craters that are elliptical on Mars could have come from an orbit around Mars's equator in its past. So we did some work and tried to basically correlate the direction, so the azimuth of these craters, with the orbit plane that they could have come from, but also taking into account the fact that Mars's rotation pole might have changed over time. because we know that volcanism has happened and various other things have happened. Mars's rotation axis might have shifted over time because its mass distribution changes. So that means that, okay, you can look for, if you find 3 craters that all have the same orbit plane, that doesn't necessarily mean they all came from the same orbit, because if they happened at different times, Mars's rotation might have been in a different place. So then you have to put Mars's rotation pole at all the different places that it could have been and figure out how many craters align with that orbit. Anyway, the short story is we found a few places where there are, I don't know, between 2 and 5 craters that line up with a kind of ancient rotation pole. So they would have formed from Mars's equator. They would have kind of spiraled inwards from a debris disk that could have been formed by a giant impact.
That's cool.
But it's a bit tricky because there's a lot of uncertainty. Mars has been resurfaced a lot. This would have happened a long time ago. A lot of degradation could have happened in that time. There's some uncertainty on the azimuth of the crater. So if you're looking at an elliptical crater, but it's 4 billion years old, there's all kinds of degraded parts of the crater rim. So how do you know precisely which direction it came from? So there's some uncertainty in that. But it's an interesting hypothesis, and it also extends to other planets.
Yeah, I was going to ask, like, to what extent can you use the Moon and Mercury and places like that to try and test this as well?
Yeah, so that's on the cards at some point.
Would
unless somebody does it before me.
Would for Mars, would the moons of Mars affect this in any way? I mean, do we get a sense of how, when assuming the Martian moons were captured, would that affect the sort of orbital dynamics at all, or are they completely different times?
Well, the moons might be leftovers from that.
Right,
that's the question, right? Are they captured asteroids, or are they leftovers from a debris disk? And that's really the question that spurred this project. Because if we can show that there was a big debris disk where multiple of these elliptical craters came from, then maybe, well, basically it adds support that Phobos and Deimos might have come from that.
Yeah. And do you have any theory of what size the impactor would have to be, and therefore potentially what crater might be the leftovers from what released the material in to form this disk?
Yeah, I mean, it was pretty big. So off the top of my head, I'm not sure, but there were only a few really big impact basins on Mars that could have produced a disk that size. So, like Hellas, for example.
Oh yeah, Argea potentially, something like that. Right. But
so it would have been something pretty huge.
Yeah, fair enough.
Can you date these elliptical craters? That might be a naive question. I'm not really but you said they're old. Can you tell if they're all the same age or different ages?
Well, that's another part of the question, because you don't. The way you date them is with counting craters on their ejector blankets, right? So you can constrain their age if you know the geologic unit that they're on, because that's the maximum age they can be. But then you can pin down their age a bit more if you count the smaller craters on their ejector blankets. But on Mars, there's an atmosphere, there's other resurfacing. Small crater populations are not necessarily, well constrained, and then really not useful for really ancient stuff, because the surface has been resurfaced many times for ancient stuff. So then how do you tell how do you constrain age when something is really old? Well, you need big craters, because those are the things that populate the ancient part of the crater chronology curve. So, but there aren't any, because these elliptical craters are quite small themselves. They're a few kilometers wide. So yeah, it's difficult to constrain their age.
I guess the size of those elliptical craters at least gives you some information about what the size of the material in this debris disk will have been, because
and most of them would have needed to have impactors that are a bit smaller than Phobos or Deimos. And there are some papers that show that actually there are models that would be consistent with that, because the leftovers of a debris disk tend to be much bigger than the stuff that just fell back to Mars's surface. So you can think about stuff that's up to about 2 kilometers or so wide, but most of it would have been 500 meters, 1 kilometer or so.
I like the idea of a 500-meter lump of rock being small.
Tiny.
Just a little blip thrown into space.
Yeah, not much effect.
So let's say hypothetically there was this disk. Would the theory therefore be that all of it fell back down to Mars and that's why it's no longer there? Or
well, if it existed, then it doesn't now. So it went somewhere.
Yeah. Oh, that's a good answer. That's a good answer.
And if it went somewhere, where was that somewhere? Probably Mars.
Yeah.
Would have Mars's atmosphere been thick enough for a lot of it to have burnt up? I suppose that must have a constraint on the size of the impactor as well.
Yeah, it's a good point. So if you look at the speed that you need to be in a Mars orbit that's circular at a particular altitude, I don't know how fast you would need to be going to actually burn up. Certainly for big chunks, they're way too big to burn up.
Yeah.
There's just not enough energy imparted to them to, fragment and destroy them on the way down. So actually, the question then is, what was Mars's atmosphere like 4 billion years ago?
Yeah.
And that's another big part of it. So a separate section of this work is to look at, if you have a particular impactor of size and density, whatever, and you throw it into an ancient Mars atmosphere, how much drag does it experience? And then what's the resulting angle of the impact? Because actually, maybe if there was a pre-disk, but there was a 500 millibar Mars atmosphere at the time that they impacted, they were coming in quite shallow, but then because of the atmospheric drag, they basically just fell straight down much more slowly. Yeah. And then they wouldn't have produced any elliptical craters.
Yeah.
So lots of parameters.
Yeah. Is it quite frustrating? Because it sounds like you've got a lot of parameters that are still quite open-ended, but we don't really know the exact answer to. It must be quite frustrating trying to pick out some of these assumptions to try and get to the bottom of some of your key questions.
Yeah. I think, and please stop me if this is too philosophical. I think there are really two approaches to science and making discoveries. One of them is to take the parameter space of possibility and publish something that is not impossible and call it a result. And that's fine, because that's the theory and it has credibility. And another way is to narrow down the parameter space and publish that narrowing and say, well, look, now we know what's impossible.
Yeah.
So there are kind of two sides to it. And in this case, it's kind of in the middle, because there are some things we can't narrow down, but nobody's really reported on any of the boundaries yet. So might as well do that.
Yeah.
Our not so surprise final question for you, Elliot, is if you could be doing something else completely different, either in academia or outside of it, what would you want to do?
Now, I think last time you chatted about drums, didn't you?
Yes, I did. I think that's still true.
You've been able to keep up with drumming during lockdown, much to the annoyance of your neighbours?
A little bit. So yeah, I mean, I have an electric kit at home, so
okay.
I practice on. But actually, lockdown has given us a chance to try, remote rehearsals. So obviously, video conferencing is wonderful, but the audio delay doesn't really work for rehearsals. But there are some bits of software that you can use that have a much lower latency, and then it's almost like you're in the same room. So yeah, I've been doing
that. So you've been managing to make it work then.
Yeah.
That's cool.
But actually, we because I live in the Netherlands, we did actually have a gig. One of the groups I play in, we played at this rehearsal room which had a stage in it, and they decided to basically have a kind of reopening gig just as the government lifted the local restrictions. But they had to put in place all of these procedures. So of course there's all those hand sanitizers and masks, and it actually really worked in our favor. It was one of those places where they give you a recording of your performance afterwards. And to keep everybody, isolated, they put a Perspex box around the drum kit, which actually was really good for the sound quality.
Yeah, I've seen that, like really kind of high-end gigs.
The
drummer's like in his own box. And
I'm pretty sure it's what Phil Collins used to do, isn't it?
Yeah, I've seen very professional gigs where that's in place, but this was very much for medical purposes.
That's cool, but no chucking of your drumsticks out to the audience then.
No, they just bounced back. I mean, the sad thing was that, they had to have the social distancing in place. So there were only like 10 people in the room and they were very sparsely distributed. the applause was much more of a tepid trickle than usual.
Yeah, and just hand sanitizer flying everywhere every time people clap their hands as well.
Yeah.
So, just before we wrap up, I guess we haven't even told the listeners, but I'm actually going to be moving over to the Netherlands in February next year.
Full disclaimer.
No way! We should work together.
Yeah, we should. Yeah, that'd be great. Yeah, it's a bit awkward. I don't want to get in contact with you really. So yeah, I'm going to be working fairly closely with Elliot. I guess just in a similar department. And yes, so I've been badgering Elliot, saying I have to jam with you when I go over because I play bass guitar for the listener. So yeah,
not actual jam, no.
No, not actual jam. Well, we'll see. So.
It's an option. I have that too.
So thank you very much, Elliot, by the way.
If Ricky gets too much, put him in the Perspex box.
Yeah, that's a good idea.
Just put him in those, you'll be fine.
Yeah.
It's sanitary from a health and social perspective.
Absolutely. Yeah. Anyway, Elliot, thanks once again for joining us. It's been a real pleasure, and hopefully we'll get to catch up again with you soon. And we'll put some links and stuff to ExoMars and other bits and bobs in the episode description. But in the meantime, thank you to everyone listening as well. If you want more from us, we're on all the social media platforms everywhere, from Facebook to Instagram to Twitter. We're at Earth Solar System. Links again will be in the episode description. But until next week, thanks for listening, and we'll see you all again very soon. Bye-bye.
Bye.